Hi everyone, welcome back. So today we're going to talk about Big Idea 6. And Big Idea 6 is all about something called reversible reactions or equilibriums. So it's a reaction that can essentially go both forward and reverse. And a lot of reactions can do that. Some can't, like combustion, fire, right? You never unburn something. But most other reactions, things like dissolving, phase changes definitely, redox reactions, all can go both forward and reverse. And it's really important for us as chemists to be able to predict how far forward the reaction's going, or how far in reverse it's going, or where it's supposed to be, or where it's at, and things like that. So we're going to talk about chemical equilibrium. All right, so these fun-looking gentlemen right here, they were the first ones to come up with the way to quantify it. They're actually brothers-in-laws, so that's kind of fun, but I don't know, maybe. All right, so first, a reversible reaction. Okay, that's a reaction which the products can reform as a reactant. Now, it kind of seems like a weird idea. We haven't really talked a ton about that in class, but a great example would be ice melting. Okay, so we have solid water and it turns into liquid water. At the same time, I can reverse that reaction and I can take liquid water and freeze it into solid water or ice. So ice can melt and water can freeze. That's a reversible reaction. And like I said just a couple minutes ago, there are three main reversible reactions. Now, there's a lot, but there are three main ones. Phase changes are one of them. Dissolving something. All right, I could let's say pop. Pop's a great example. At the factory, they dissolve carbon dioxide into the pop. Okay, so that reaction goes forward. The carbon dioxide dissolves into the pop. At the same time, when you open it up at home and leave it out, the carbon dioxide comes out of solution. So it's the forward reaction in the factory. They dissolve carbon dioxide into pop, and at home, it comes out. It's the reverse reaction. Another example would be redox reactions, like a battery. Right? You can use your cell phone all day, and the electrons are flowing from the anode to the cathode. Right? You have a flow of electrons that's powering the cell phone and everything. And at the same time, when you get home at night, you plug your cell phone in, and then the electrons are going to flow the other way and charge the battery. So that's another example of a reversible reaction. Well, the problem is it becomes really important that we need to know the chemical equilibria. So an equilibria is the rate of the forward reaction, and when it equals the reverse reaction, we call it that. We used to say that the reaction stops. So if the forward reaction and the reverse reaction are in equilibrium, meaning the rates are the same, essentially you don't see anything, right? And we say that reaction has stopped. So let's say an example would be, let's say it's your battery goes dead. That's not the best example, but we'll go with it. So the forward reaction, which was you using your cell phone battery, once it's all used up, the reverse reaction, the cell phone doesn't really charge itself. So the rate has stopped. Let me think of a better example. Or pop, right? When you open that pop, that carbon dioxide comes out of solution. That's why pop has bubbles, and that's why it's fizzy. When pop goes flat, there is still some carbon dioxide dissolved in that pop. Just very, very little. You don't really taste it. You don't notice it. That's why you call it flat. But there is some dissolved in that pop. And over time, that carbon dioxide will leave the pop. And at the same time, carbon dioxide in the air will go into the pop. So this carbon dioxide will go in and out of this pop, but it goes in at equal rates, so we don't see it. It's at equilibrium. It's when the forward reaction and reverse reaction are the same. The rate's the same. And we're going to talk about that a lot more because it's kind of a confusing idea. A reaction never ends, just the rate of the forward and reverse reactions equal out. So just so you know, arrows going both ways. This is called an equilibria or equilibrium sign. So whenever you see that, it means that it's an equilibrium. The reaction is reversible. Okay, so here's kind of what I'm talking about. I have nitrogen dioxide turning to nitrogen monoxide and oxygen, sorry. So if we think about it, notice the green line is my reactant. So as we would expect, as the time goes on, my reactant decreases, right? And the blue and red are my products, and as my products increase. Okay, that kind of makes sense, right? As a reaction proceeds, the reactant decreases and the products increase. Well, it turns out that this reaction doesn't actually stop. What ends up happening is the rates level out. All right, the forward and reverse rates equal out. So we don't see any more NO2 forming, or NO forming, and we don't see any more NO2 going away because the forward and reverse reactions equal each other out. Okay, it would be like, let's say you baked me cookies. Okay, let's say you baked me cookies, and you present me with cookies, and I start eating them. All right, you would see the concentration or the number of cookies going down. But let's say you, being the conscientious student, keep baking me more cookies, right? You don't stop, you keep baking me another batch. At some point, me eating cookies and you baking the cookies will level out, right? I will continue to eat them, you'll continue to bake them, but the rate will be the same. We won't notice a change. There will always be 10 cookies left on the plate because for every 1 cookie I eat, you bake 1 more. All right, eventually the rates will equal out. That's kind of an example of a reversible reaction rate. All right, so let's talk about what's called the law of mass action. There's a constant in chemistry. It might shock you that it's K. There's like a billion Ks in chemistry, it seems. K is the equilibrium constant. Now, this is capital K. Okay, so if we talked about the rate constant, that was lowercase k. This is capital K. All right, clearly two very different things. Now, K is the ratio of product over reactant. It tells us how much product formed and how much reactant is left at equilibrium when the reaction is essentially done, or when the forward and reverse reactions are equal. So the way we do it is it's a ratio. So it's products over reactants. So here I have this reaction, and these little lowercase letters are supposed to be the coefficients. Right? K is just my products, the concentration of my products raised to their coefficients, over the concentration of my reactants raised to those coefficients. Okay, so K is my products over my reactants raised to the coefficients. So it's C to the L, because it's LC's, and D to the mth, because M is my coefficient in front of D. Right? Now, since it's products over reactants, my units would cancel out, and K is unitless. Okay, so K has no units. So that's great news. You don't have to memorize the units for K. It's not like reaction constant K values, which are different every time. The K is completely unitless. Okay, so it is products over reactants, and we're going to practice that in a little bit. Now, since it's products over reactants, if I have a very big K value, and big K values are over 1, if I have a K value that is over 1, it means I have a lot of product and a little reactant. We call that product favored. So if my K value is large, meaning larger than 1, it is product favored. So I would have a lot of product and little reactant. Okay? So when this happens, most of it is a product and there's very little reactant left over. On the flip side, if I have K that's less than 1, all right, less than 1, I'll never have a negative K, because I can never have negative concentrations. I'll never have a negative K, but I could have a decimal. A K value that is less than 1 is going to be reactant favored. So that is where I have a lot of reactant, but very few products. Okay, so that means that I'm going to have mostly reactant and very little product. All right, so let's try a K. Let's try equation. So I want you right now to stop, pause the video, and I want you to see if you can write the K value for this reaction. Okay, so I'm going to assume that you paused it. I'm going to assume that you wrote the K value. Let's see if you know what it is. Now, K is my products raised to the coefficient over my reactants raised to that coefficient. So it's going to be NO squared, because I have NO raised to the second, NO squared, times O, times the concentration of O, all over NO2 squared. Okay, so that's my K equation. Now, obviously, if I have these concentrations, I can plug it in and I could get a K value. And that K value would tell me if I'm going to have more products or more reactants. And it also does actually a lot more than that. But right now, we're just going to get into that. Okay. Now, turns out that let's say I were to flip this reaction. So this is one way to write the reaction, but I could flip it. Let's say I have the reverse. Well, if I flip it, then I'm going to have the reciprocal, right? I right now have product over reactant, but if I flip my reaction, notice I just flip my reaction around, now I'll have product over reactant, and I ended up just flipping my K value, right? You see what happened? Where if I rewrote my equation so it goes the other way, so it's flipped, my K would flip, and the value of K would be the reciprocal. Okay, so I don't have to recalculate all K, I could just find the reciprocal of it. So the K value of the forward, the K value of the reverse is always the reciprocal of the forward K value. Now let's say I need to multiply my K value. It's kind of like Hess's law, where we talked about how if I do something to the equation, I do it to my delta H value. Same idea here. If I do something to my equation, I do it to my K as well. So let's say I were to multiply my equation by a half. Okay, notice, so I get rid of all these 2's and I have half of an O2. So I just multiplied all of these coefficients by 0.5. Well, then I would do the exact same thing to my K value. Right? I would raise it to the 1/2 power. Right? So just right up here when it says when a balanced equation for a reaction is multiplied by factor n, it's raised to the nth power. So I multiplied this by 1/2, so I raised it to 1/2. If I were to multiply by these by 3, I would cube my K. And then they just put K 1/2 to differentiate between K and the original K and half of that, or K 1/2. Shouldn't say half of that because you're really raising it to the half, but whatever. All right. Now, with pressure, I can do this for aqueous solutions, and I can do this for gaseous solutions. Now, for gases, it's the exact same thing, but technically you can't have a concentration of a gas, right? Concentration is moles per liter, and gases are measured in atmospheres or pressure. So it's the same exact thing. It's the same exact thing. Here's my equation, right? My K value is the same exact thing, except it's just P, the pressure of NH3 squared, over the pressure of N2 times the pressure of H2 cubed. So it's just the pressure of it. P stands for pressure. And as a result, my K value is K sub P, or the pressure equilibrium constant. Okay? I can put little sub things here to tell me what the different K values are. I could do K sub A, which would be acid, or K sub B, which would be base, or K sub P, which is pressure. And they're all different K values. Okay? Now, we will get into this a little bit later in our next lectures. We're not going to really talk about partial pressures quite yet. All right. Okay, so we are nearing the end of our time. We just have a couple more slides left. Now, it turns out that equilibrium are based off of gases or aqueous solutions because pressures can change, concentrations can change, things like that. It's not based off of pure solids or pure liquids because I can't change the concentration of pure liquid. The concentration of a pure liquid can't change because I can't dissolve it in, if I were to dissolve it in more water, it'd be a solution and not a pure liquid kind of thing. What I'm saying? So, for example, let's say I have this equation. If I have this equation, PCl5 turns into PCl3 plus chlorine gas, I do not base my K value off of the solids or the liquids. PCl5 is a solid, PCl3 is a liquid. I do not base my K value off of pure solids and liquids. Therefore, and that's a therefore sign, therefore, K is just the concentration of Cl2. That's all my K value would be. My K value would equal the concentration of Cl2. Kind of, not quite, because Cl2 is a gas, right? So it really, K would be the pressure of Cl2, not the concentration. All right, minor difference, tweak. Most AP readers don't really care that much between brackets and P for pressure, but I thought I'd, do it anyway. All right, so that was the end of my presentation. I hope you understand now what K is. K is a ratio between products and reactants, and it tells me how much product versus how much reactant formed, or how far my reaction went before it reached that equilibrium point. All right, I hope everything's going well, and I will see you in class.